Hi everyone, my name is Milad and today I'll be doing a system design practice exercise. In this video, I'll be designing Shazam. Shazam is an application that allows users to find out the name of a song by listening only to a few seconds of that song. Some of the things that are granted is it will be a black box model for determining songs. That means we can just treat it as service. We don't have to dive into the details. And we should know that a song is converted into multiple fingerprints, each fingerprint consisting of up to 100 characters. Let's start off with our non-functional requirements. We definitely want it to be highly available. We definitely want it to have low latency, and we want it to have eventual consistency. These are a couple of requirements we can start off with, and we can always expand on that. Our functional requirements will be sign up, login. We will allow users who have not signed up to find 10 songs, after which they have to sign up. We want users to be able to upload song clips, view song details, and view albums the song appears in. Alright, that is a great start. Next, I'd like to figure out what kind of data I'm working with. This gives me an idea of the entities I'm going to work with. And to do that, I'm going to build my database schema. But to figure out what database schema I'm going to design, I have to figure out what kind of database would be most appropriate here. And given that we are going to have data that can take advantage of relationships, a SQL database would seem really appropriate here, and as well as utilizing Redis. So for our database schema, we'll be using tables and columns. We'll start off with user table. Then we will have song fingerprints, and then song albums, and let's try to think here, and I think that's a great start here. We can dive into the details of this later. And let's dive into our API. We want to post here for sign up, post for login, and we want to post song clip. We also want to get song. Over here we would be sending file. Over here we will have our parameters. get album ID. All right, let's make sure we are satisfying our functional requirements, allowing the user to sign up and log in. We've taken care of that. Users who have not signed up, that won't really require a specific API endpoint. Simply will utilize post, upload song clips, so this is this function. View song details, this is that function, API endpoint. And view songs, view albums the song appears in, that'll take care of the get song endpoint, will also take care of that. And then view album. All right, next let's dive into our general flow for the application. For a service like this, I'm going to lean on microarchitecture because there are areas of this application that will require larger scale than others, and this approach allows us to scale them independently. We'll be focusing on a couple of areas. User control, search control, add song control, process song control. All right, these are our high level view of the different areas we'll have within our system. Let's start off really simple and go after the user. To control access, we'll use OAuth. This allows users to sign in using third-party services as well as our own internal sign-in login option. When a user signs up, let's get rid of this. We'll have a user service. User logs in. Our OAuth service will communicate with the user service. Then create a session. Next, what we want to do is also going back to our functional requirements, limit users who don't have an active session to 10 songs. So we can have a service that says non-session, let's say limit service. And if we go to our post, we will either have an access token, and if that's absent, well, regardless of whether that exists or not, we will also have an ID. Depending on whether they're on a desktop or on an app, we can use different ways to generate those IDs. And so if a user is not logged in, we will hit the limit service. Then we also want to take care of our user information. So we will have our database here. User service interacts with the DB as well as the limit service. Since one of our requirements is low latency, we want to use a faster service than a database. And to do that, we utilize caching. Because we want our system to be scalable, Redis is a good option here. Has a lot of built-in scalability and other features that can help us maintain high level of performance. So both the user service as well as the limit service will utilize Redis. We'll dive into the details of this later. This is our API gateway. Okay, next we want to take care of our search control. This requires us to find a song. So we will have song service. This song will take the clip and pass it into our model. The model will spit back a fingerprint, and then we will look up this fingerprint in our quick access cache. If it doesn't exist there, we will check our database and return the results. We will get in our Redis, we will have a key value pair that will have the fingerprint and the song ID. Next, we will have song album service. This will handle the get statements. It will search our Redis server. Then if it doesn't find anything in Redis, it'll look in our database. That takes care of that. Next, we want to take care of adding songs. upload service. We will have two ways of uploading. Through a gateway where we create an admin panel on the back end that allows administrators to upload, and we will also have third-party servers. We'll create a job that will run daily, check the third-party service, and then upload it to the upload service. Likewise, if we're uploading it directly, we will upload it. We will send it to the upload service. Because we're dealing with media, and those files can become quite large, we want to use a blob storage. We'll set something up that will hold the files temporarily. And then once that file has been uploaded, we will want to process that song. We will also save that information in our database. And then pass it on to be processed. Over here, we will start the process control. So, one of the keys to a scalable system is decoupling services that do not need to be coupled. This allows us to independently scale services that might require more processing time. So to do that, we create local scalability through a messaging queue. Now there are many messaging queue services out there. And basically what happens here is we write a message to this service, and then we have subscribers that will listen to these topics and take action based on those messages. So now we will have process song service. Which will subscribe to this topic. It will then have our model. It will send the song to the model, and then the model will return the fingerprints, And then what we do is, once again, we want to decouple the service from any downstream service. So we'll set up another messaging queue. We will write to those. The process song service will grab the file from the block temp storage for processing, and it will also communicate with the database to indicate that the file has been processed. We will have another blob storage here with TTL. Because we have no use for the raw raw song in the long term, we can decide to delete them after a while. So, we will have a move file service that will subscribe to a specific topic here, and it will grab a file from a temp and save it into our long term. It will then update our database with the most appropriate, with the new file location. Next, we will have service called gas service. This service will subscribe to this message, to this messaging queue, to a specific topic, and then it will also listen to database changes, and then upload the latest information to our Redis service. So this is what our system would look like on a very high level. Now, when we talk about scalability, we have local scalability using messaging queues, allows different processors to be decoupled. Other things we can take into consideration are load balancers. The number of layers we need will depend on the scale we are trying to satisfy. In addition to having multiple load balancers and multiple data centers, at each specific data centers, we can have elastic infrastructure. So we can use something like Kubernetes to scale different services depending on usage of the CPU and memory. For our database and Redis, we will consider providing them as a service, creating clusters for redundancy and fault tolerance. And then for optimization, we want to think about partitioning as well as sharding for our database. In terms of routing data, given the scale that we will be dealing with, it will determine the type of routing we want to do. One approach would be consistent hashing. Consistent hashing allows us to direct data to a specific node And then those nodes themselves can be sharded for additional optimization if that is necessary. And for our database, we would probably add some indexes. For our cache, we want to make sure that we have the right number of partitions to take care of the load. And then for our messaging queues, depending on the number of subscribers and publishers we have, specifically subscribers, will partition each topic accordingly. Alright, everybody, that's how I would design Shazam. I hope you found this video useful. And if you did, please leave a like and a comment below. Thank you so much.